congratulations, you made it here. And you are one of the few lucky that can witness this historic event. Or well, it hasn't happened yet, but I'm pretty sure it's going to happen soon. And that is the birth of a new product, which I'm going to call Control MC. This product is for people who has an old motorcycle or a damaged motorcycle, or for one kind of reason needs to rewire their motorcycle, maybe to modernize it or to repair it. And I'm going to build a motorcycle computer, which is unique. Nothing like this exists. It's going to be flexible and programmable, open source. I'm going to share all the parts and how it's done. And if I succeed, I will also make a pre-built configured kit. So for those who are not DIYers and want to do everything themselves can also get the solution. Okay, it's not quite correct to say that the historic event starts now, because it's actually almost 4 years ago. It's exactly 3 years and 10 months since I first started this project and posted this YouTube video. It's time to take a look at the wiring for my cafe racer. It's just one thing to say about this diagram. It's a perfect representation of the spaghetti cabling. This looks way more complex than it actually is. I guess you've already noticed that I'm not very happy with this. I have decided to make my own. In my diagram, the top part represents the front of the bike and the bottom part is the rear of the bike. In the middle of the diagram there is a front and a rear computer with some wiring in between. It receives input signals from all the handlebar controls and sends it to the rear computer through a communication cable. The rear computer takes care of delivering current to all of the bike's components through a relay. It's just one problem with this. This computer does not exist. Well, that is not going to stop me, so I will build my own. Let me show you what I've done so far. What you see here is on this side is the unit that goes on the handlebar, and on this side is the unit that goes in the seat tray. Maybe this can be big. All right, I will be the first to admit it. The progress hasn't been impressive. But something has happened during these years. Most of it's inside here. I have been researching, buying parts, testing out stuff, doing system development, learning more about electronics. So the first plan I made 3.5 years ago, it's slightly changed over the years. More about that later. In this video, I'm gonna restart the project, start all over, but I'm gonna build upon the experience I've gained and the first prototype I made back then, which looks like this. First, let me explain this control system. To the left is the clutch lever, then the turn signals, high-low beam. Then it's the multifunction display menu buttons, start-stop button, and all the way to the right, the brake lever. None of these buttons work now because the ignition is off, except one specific button, which I have programmed to start the password check. This is my keyless solution. When you see this symbol, you can enter the password you have set up in the system. Now the ignition is turned on, and the display is showing the status page. Let's test the turn signals. And here you can see the relay in action. The handlebar unit is now sending the signal to the relay unit, which is triggering the relays on and off. Let's go into the menu. Here I can turn on the lights, park, and then low lights, and then you can turn on the high beam and low beam. And if you go into the menu and wait for a while, the system will automatically go back to the status page. Let me show you how to turn off the bike. Use the menu selector, then to the ignition settings, and then select to turn off. And then all the buttons will be non-responsive until you turn the ignition back on. I still have some of the parts from the first prototype. And I even made a relay unit for controlling the motorcycle with 10 relays. But none of this is going to be used. Everything's gonna be much better and much more upgraded. Maybe you can see here a little box from JLCPCB, I've actually started creating my own PCBs, stepping up the project a bit. But for now, I will be using this breadboard, temporarily boards to plug stuff into to test out. But before I start working on the electronics, let me tell you a bit about the concept and why I have changed it. It all started with my cafe racer project. Not this motorcycle, but I do have a Honda CB400 cafe racer, and the whole idea was based around that project. And for my cafe racer, I have deleted the original instruments and I want to replace the handlebar controls. And that's why it made sense for me to make a new display unit here at the handlebars. And I have planned a relay unit under the seat for hooking up all the cables. And then only a signal cable between those. And I wanted to fetch all the signals by sending them to the display unit, maybe even the speedometer signal, maybe even the RPMs hook up to the coil or something. And also the rear unit can fetch some of the signals. But this was not a good idea, because what if you want to keep all the original stuff? And what you really only want is some way to help out with the wiring, and you only need the relay unit. So, my new idea is like this. I want to make a flexible system. So, if you want to just do some small improvements to your wiring on your motorcycle, or if you want to do a big improvements, replace everything, if you want to go digital and have new instruments, or you want to keep it retro looking, all the original controls and speedometer, and just want to have a better wiring system, I want to solve all of this with a very flexible system. And I think using a CAN bus, a network signaling system, so that CAN bus is short for controller area network. So it's like a digital network that you use to send signals through cables. And it's used on vehicles and in a lot of industries. It's a reliable system. And the benefit with it is that you don't need one central hub or part to control it. So a car normally has a lot of ECU, electronic controller units, and each of them can have its function. And if one of them doesn't work or is shut down, the other will still work. So I think having a lot of small components, you want to try to normally tuck away the electronic part on a motorcycle. You don't have too much room often. So making small components that you can put together with the cabling that doesn't occupy too much space, that has to be a genius way to do it, isn't it? For instance, if I'm going to rewire my whole motorcycle, think of the rear part of the motorcycle. I have some lights there. So I need an output unit there to send current to my rear taillights. And then I need some way to hook it up to the battery. So I need some battery input module with some fuses and some power management. And then I need to fetch some signals from the engine and from the brake pedal and the gear shifter, oil pressure sensor, maybe water temperature. And then moving forward on the bike, we have headlight and the turn signals and all the instruments at the front part of the motorcycle. So I need an output unit there as well to send current to these parts. And then I have the instrument, which might be a new digital unit, or maybe the old one, and you just need an output unit to the indicators on the dashboard. So by adding a lot of these small components, just plugging them into the network with the input and the output cable, you can have one cable going along the motorcycle and adding up the units you would like. I think this could be a nice idea, but still early phases. Even though I've been thinking about this for almost 4 years, I need your input. Is this a good idea? Is this something you think could work? Do you have some experience from rewiring your whole motorcycle or part of it? What would be your dream system to simplify the wiring or to modernize the motorcycle. Remember, I want to have it flexible. Think of your specific needs, but also think of what others might need. I'm not really sure how this goes yet, but one thing I know, I need a speedometer on my adventure motorcycle because it's broken. I've redone my instrument panel and I need just a tiny small speedometer. I think that is the first thing I'm going to tackle, just as an easy startup project. And I've already prepared a prototype for the speedometer, and it consists of 4 modules: the display, the microcontroller, power module, and a Hall sensor that is going to be attached to close to the wheel to measure the speed. And what you can see here is just some few of all the components I have bought to test out and figure out how I'm going to do this. And this is sometimes just called the modules, and other times it's called development boards, like this microcontroller here. These are made so they can just be plugged into your PC or Mac with the USB cable, and then you can do development and test them out. But of course, when this is going to be put on my motorcycle, I need to power it from the motorcycle battery. That is why I need this power module. So these cables is coming from the motorcycle. I am using a adjustable power supply here. So I set it to 12.5 volts, simulating the motorcycle battery. These 12.5 volts need to be stepped down to 5 volts. And this power module, it also has some power protection features in case of a spike and to ensure that the power that is put to the microcontroller is no more than 5 volts. This microcontroller normally runs on 3.3 volts or 5 volts, so you need to step down the voltage to the microcontroller. I made this housing very early in the project. I thought maybe this could be possible to mount on my cafe racer, but it's really too small. Inside here is this small display unit. I started out actually with an even smaller one, less than 1 inch. These are too small. I have now selected this one. I will also be testing out circular round displays, much cooler at least for the cafe racer project. And I've actually also ordered from Garage Tinkerer a 2-inch circular display that looks very promising, 1000 nits, so it's very bright. These displays I'm going to test out now is OLED, so they have a good contrast. I think they are bright enough. The last piece here is the Hall sensor. Let me power this on now. Here the display is starting. Okay, the display has some strange readings here. I can see one of the cables are really loose. That is the big issue with this prototyping when you're using these development boards and all these cables and these breadboards to plug it in. Some of the cables may come loose. It's very, very tiny margins. Just a tiny little blip and the program gets out of sync. I think I'll just put on a dab of tape here to hold it. And I think this could be a suitable time to tell about this video series sponsor, JLCPCB. The problem I'm struggling with here is going to be solved as soon as I get all my components securely soldered to a PCB. When I first started this project 4 years ago, I thought there was no way I was going to ever build my own PCBs. That was definitely for the pros. That was my thought. But it's really not that difficult, and especially using the self-service systems that JLCPCB has provided, it makes it easier than ever to order your own PCBs. I have been using a software called KiCad to design my PCBs. From there, I export a Gerber file, which I can just drag into the order page on JLCPCB's website. Here you can actually see my next PCB, which is a CAN bus controller. That is going to be pretty cool. But now let's focus on the PCB I've already made. As long as it's just the PCB you're going to order and not with components, it's not much you need to do here. I of course have to select a black color on my PCB, which is my favorite color, before you go to the checkout page where you can select different type of shipping. You can get it in a couple of days if you select a fast shipping, which is pretty expensive up here to Norway, but there is also a more reasonable shipping option if you can wait a while. But let me get back to how the speedometer is going to work. The whole sensor is connected to the microcontroller, which is sending a constant stream of current through it. And when a magnet gets close to the sensor, it affects how much current is sent back to the microcontroller. The display is not showing the actual voltage that is coming from the sensor. It's just a number from 1500 to 3000, indicating how close the magnet is. The microcontroller has also a timer that is very precise, not only milliseconds, but actually microseconds. And I'm using this in combination to the magnet to calculate the speed. Okay, so in theory, this should work. It's just to put it out in real life to make this work on the motorcycle. One big issue is electrical noise. I have here now just 10 centimeters with cable from the sensor to the microcontroller. On the motorcycle, the sensor will be at the hub of the front wheel, and I will have about 1 meter of cable up to the instrument on the dashboard, and that can cause electrical noise to interfere with the signal. It would have been better to have a more powerful sensor. I have a bigger sensor board. This one can take 12 volts, can actually take up to 30 volts. And having powered the sensor with a higher current would have given, of course, a stronger signal to read. But then I can't read 12 volt directly from the microcontroller. Then I would need some more finicky stuff to take the 12 volt down to 3.3 volts, which is the maximum that the controller can handle. So then I would need some decoupling of the power and read it that way. So I'll just try out now with a long cable to see if it works or not, just as an experiment. If it works, that's definitely the easiest. I will also need to refine the software. I made my own font that I think is cool, that is bigger to display the speed. And I will also calculate the distance traveled in kilometers, some trip counter, and maybe also a timer. So I can add a bit more features to the software. It's not that difficult to program these microcontrollers. But first most, let me focus on the hardware. This is all the pieces needed for building the speedometer. In addition to these 4 pieces I've already shown you, I have some connectors and some electronics for an extra power supply. This is a 3.3 volt power supply dedicated for the display. This big one is a bit more power hungry than the small ones, so I need a separate power supply for it. I'm using these holders from PCB to hold the PCBs while I'm soldering it. They are spring loaded and they have a magnet underneath. So if you can see here under my silicon mat, I have a metal sheet. Everything is included in the kit from PCB. Highly recommended. So I can securely hold the PCB while I'm soldering it. My custom PCB is very simple. It acts like a motherboard to plug in the other components. The ESP32, the microcontroller, plugs in on the right side, and the power supply goes to the left. Then the connectors go in the front part. I have a dedicated one for the 12 volt input power, and then a bigger one for all the input-output signals from the microcontroller. And I also have a spare ground connector, just in case. This is all the parts that goes on this side of the PCB. On the other side goes the display and the power supply for this display. If I turn it around, you can see all the pins I need to solder. But I will actually start with soldering the other side first. Here you can see how the display fits on this side, but the power supply for the display actually needs to be soldered on first, because that goes underneath the display. So the first and challenging task is then to solder on these tiny small parts, which is not the easiest job for me with my shaky hands. But I'll do my best, and you can give me feedback if I did a decent job. This is a LDO, a low dropout regulator, with a capacitor on each side. This type of regulator provides a very stable current, very good for electronics. To give myself the best possible foundation for a successful soldering, I start by cleaning the PCB with isopropanol. Then I add a dab of flux on each solder point. It's a cleaning agent that reacts to the heat from the solder iron and makes sure that the solder is bonding properly to the PCB. And as you can see here, I'm learning by doing. I found it best to just put on flux on the pads you're gonna solder on one by one. So cleaning everything, and then it's time to solder on the components. And that's actually the second historic event of the day. Somewhat, at least for my part. First time I've ever done surface mount soldering, and at least on my own made PCB. How do you think I did it? Well, is it okay if I did any mistake? Please let me know. Next job is something I've done before, and that is to solder on these true hole components. They are a bit bigger, should be easier. I will not actually solder on directly the component for this first prototype. I have these holders that I will solder on, and then I can plug in the components into the holders. And this is only for the prototype, not for the one to be permanently put onto the motorcycle. For that one, the components will be directly soldered to the motherboard. It has actually been a couple of days now since I soldered the speedometer. So I've done a lot of work off camera. So now I'm gonna get you up to speed. It has been some kind of a roller coaster the last 2 days. A lot of struggle, but some successes as well. First of all, like just to have this chunk of electronics soldered and solidly put together is so much better than dealing with this breadboard and all the cables that is sometimes working and sometimes it's not working. Much more stable, easy to work with when I have this soldered into my motherboard. That's a total success. I had some fun as well. For instance, my electrical drill. So I 3D printed this wheel to attach to my drill, and with a slot where I inserted 2 of these magnets. A wheel simulator. So this simulates me driving with a motorcycle. The magnet rotates so I can measure the speed more realistically. That's been working great. What was a big problem was this hall sensor. I attached this long cable, and this hall sensor, it has the type of the sensor is 49E. It's an analog sensor. It measures the distance from the magnet and to the sensor. And it was just impossible to use. It was so much electrical noise, I couldn't get a proper reading. Luckily, I had a couple of different other sensors, and I found one very similar to look at, but this is a pure digital sensor. It has a sensor called 3144. Make note of that if you're ever going to do something like this. I have a similar long cable here. I've just put a sleeve over it. It is 1 meter and 30 centimeters long, and it works finally perfectly. This sends not a variable signal. You can't detect how far away the magnet is to the sensor. It's either sending 3.3 volt back to the microcontroller when the magnet is nowhere to be seen, and when the magnet gets close enough, it shorts to ground and it sends 0. So it's either like 0 or 3.3, and it's much easier to detect when the magnet is there or not. I can also mention I had to rewrite all the code because this is total different method to read this sensor compared to the first one. Most of the code I made had to be scrapped and built from scratch, and I ended up using an interrupt. If you're into the programming part, interrupt type rising, so I'm actually detecting when the magnet is leaving the sensor. That was what I found was most reliable. So when the magnet is getting into the range, I do nothing, but when it leaves and starts the next rotation, then I trigger an event. And I use a pull-up pin as well, and the combination with pull-up and rising. If you want me to dive into the system development, let me know. I can make a video about that as well. System development is what I know most. The electronic parts I'm learning. But enough of this boring talk. It's time to test it. Make a demonstration here. Let me power it on. And this is how it looks like. Okay, there you got it. What you see now, what I built, is with a big, my new font here, it's the speedometer on top. I have a timer. It always starts on 0. This is how far I've been riding since I started the system. Then it's a trip counter and a total counter. I can just set an initial number here. So when I am starting to drive, let me then use my drill here as a wheel and see what happens. Very nice acceleration here. Let me speed up. Alright. This is the maximum speed of my drill. Alright, so you can see it works pretty nice. So now I've been running here for over a minute, 1 kilometer on this session. On the trip counter is 4.6, and then the total at the bottom. If I now turn off the battery, I'm stopping the bike, disconnecting it, and when I'm powering up again, it's pretty responsive. Quick boot, and you can see it continues. The session starts on 0. That is like the length for this trip. And then it's since the reset, and then it's the total. But of course, I am missing a reset button to reset the trip counter. So I would like to attach a button on my handlebar or close to the display so I can reset it. Of course, I also need to make a housing, an enclosure for it. I have made a small enclosure for the magnet, 3D printed it, and inserted a magnet midway. So I have an enclosed magnet here. And I can't attach this sensor here directly onto my motorcycle. So I have made an enclosure for the sensor, so it is a bit protected. And then this can be attached on a fork close to where the magnet is on the wheel. But I think that's it for today. Some kind of a success. It's working exactly as I hoped for, but will it be working on my motorcycle in real life? That would be in my next video, trying to put this on the motorcycle and test it out and see if it works in real life. Hope to see you back then. Bye bye.